Section 7.5 is concerned with the strengths of ionic and covalent bonds. First of all, we'll look at covalent bonds, and then we'll look at ionic bonds. But it's important to realize that whatever the type of bonding involved, there are two factors that affect the strength of the bond. First of all, short bonds are strong. And that really holds for any particles that are interacting. The closer they are to one another, the stronger the interaction. So that works for magnetism. You probably noticed as you bring magnets closer together, they interact more. It works for things like gravity as well. The closer two objects are, the more their masses interact. The next thing to realize is that all bonds are a result of attraction between oppositely charged particles. And what this means is bigger charges produce stronger bonds. So whether electrons are being shared or whether electrons are being transferred, the more charge involved, the stronger the bond. And if you keep those two ideas in mind, you'll go a long way in understanding this section. So first we're going to talk about covalent bonding. And for a covalent bond, we can define what's referred to as the bond order. And this is just simply a measure of the number of electron pairs that are being shared. So if we have two electrons being shared, then we have what we call a single bond, right? And a single bond has bond order 1. If we have two electron pairs being shared, we have what we call a double bond, and that gives us a bond order of 2. And if we have 6 electrons being shared, we get a triple bond, and that has bond order 3. So that's a pretty simple idea. And as the bond order increases, the bond strength increases because the number of electrons, the amount of charge that is being shared, is increasing. So we can see this in this table here. What we've got is different pairs of atoms, and you can see that as the bond order, the bond strength increases, the bonds get shorter. So for a given pair of atoms, the higher the bond order, the shorter the bond, which is consistent with what I mentioned in the intro slide. You might want to answer some questions, look up bond energies and bond lengths, and you'll find that information in table 7.3 and I think also in table 7.2. So again, we'll see the same trend with the bond energy. As the bond order increases, going here from a single bond, double bond, triple bond, you can see that the bond energy goes up as well. And that applies to any pair of atoms. So whether it's carbon with carbon or carbon with nitrogen, as the bond order increases, the bond energy, that is the energy required to break the bond, goes up as well. And again, in table 7.2, you can find a big old list of bond energies if you need that. So, bond energies are sometimes referred to as bond strengths. What these represent is the enthalpy change, or the delta H, that occurs when a mole of bonds is broken in the gas phase. And it's important to recognize that bond forming is always exothermic and has a negative delta H, which means that bond breaking always requires an input of energy and will always be an endothermic process and have a positive delta H. So that can help you when you're calculating these things to check that you got everything around the right way. I tend to refer to bond energies as enthalpy changes. Some people will give them the symbol uppercase D. Your book does this. A D represents the dissociation energy. So that kind of makes sense. Dissociation means to break. So it's the energy to break a mole of bonds in the gas phase. These tend to be average numbers. So the carbon-hydrogen bond in CH4 might have a slightly different bond energy than the carbon-hydrogen bond in C2H4, but they kind of average them out over a bunch of molecules. So bond energies are often used in conjunction with Hess's law to calculate the enthalpy changes for reactions. So if we have a reaction like this one here, which is the combustion of methane in oxygen to produce CO2 and water, we might want to know what the enthalpy change for that is. Now, this is a combustion reaction, so it releases a bunch of heat. So it's worth noting that this enthalpy change will be a negative number because it's an exothermic reaction. Now, what we're going to do is we're going to consider the reaction to occur in two steps. In step one, what we do is we take all of our reactants and we just break them apart into individual atoms. There we go. Okay. Now, the enthalpy change for that process would be the sum of all of the bond energies for the bonds that we're breaking. So we're going to be breaking 4 carbon to hydrogen single bonds, and then we're going to be breaking 2 oxygen to oxygen double bonds. So if we added all of those together, we would get the enthalpy change for step 1. Now, in step 2, what we're going to do is we're going to take this big pile of individual atoms and we're going to reassemble them in the form of the products. So instead of breaking bonds, we're going to form bonds, right? And so all of the bonds that we're going to form are these guys. So we're going to form 2 carbon to oxygen double bonds, and then we're going to form 4 oxygen to hydrogen single bonds, right? Now, we don't have a table of energies for bond formations. What we have is a table of energies for bond breaking, but it's okay because breaking is just the opposite of formation. So what we're actually going to do is we're going to add together all of the bond energies for what we're forming, but then instead of like adding that, what we're going to do is we're going to subtract that to the enthalpy change from step 1. So we're basically just going to reverse it, right? Because the opposite of bond breaking is bond forming. So instead of just like adding those two sums together, we're going to subtract one from the other. So what we end up with is this, right? We can use a table of bond energies to estimate the enthalpy change for any reaction by adding together the bond energies of all of the bonds that we're breaking. These are our reactants. And then subtracting that from that, all of the bonds that we're forming, which are our products. Now, the only thing is you've got to really kind of like make sure you calculate that you count up the correct number of bonds. And sometimes people get that wrong. So in this case, as I mentioned, we're going to have 4 carbon to hydrogen bonds, and they are single bonds, and we're going to have 2 oxygen to oxygen double bonds, and then I'm just getting those bond energies from the table. So that's my enthalpy change for step 1. For the second step, we're going to add together all of the bond energies for what we're forming, right? So in this case, we're forming 2 carbon to oxygen double bonds, and we're forming 1, 2, 3, 4 oxygen to hydrogen single bonds. So when we add all of that together, that's what we get for the sum of all of the bond energies for what we're forming. Now, when it comes time to calculate the delta H for the overall reaction, we need to do the sum of what we're breaking minus the sum of what we're forming. And sure enough, just like we were hoping, for this particular reaction, we get a negative enthalpy change. And there it is, minus 808 kilojoules. So the only tricky bit is sometimes people rush things and they don't count up that correct number of bonds because they forget either about a coefficient or they forget that a molecule might contain multiple of a given bond type. Okay, so that's all we're going to do for covalent bonding. Now we're going to talk about the strength of bonds in ionic compounds. And the general way that people will talk about the energy of the interaction between two ions is to use what we call the lattice energy. And the lattice energy is the energy released when two ions form an ionic bond in the gas phase. So the lattice energy describes the energy change when 1 mole of an ionic compound is formed from the gas phase ions. So this would be it. And it's normally a really big negative number because, well, we're forming very strong ionic bonds. That's why it's big, and it's negative because it's bond forming, not bond breaking. Now, the lattice energy depends upon a couple of things. For every compound, there will be a characteristic constant that's describing, that sort of summarizes how the ions are arranged in the crystal. It depends upon the distance between the ions, which is simply the sum of your cation and anion radii. And unsurprisingly, as distance goes up, the bond strength goes down. Because remember what we said, the further apart these things are, the weaker interactions are going to be. And then it also depends upon the product of the charges of the ions. And what we can see here is that we have bigger charges, then bond strength goes up, and that's exactly what I was saying in the opening slide. So that's pretty much like how the bond strength depends upon the properties of the ions. The general rule is big charges give strong ionic bonds. So +2 ions interacting with a -2 ion is going to be a stronger bond than a +2 ion interacting with a -1 ion. And then the next thing is the sum of the ionic radii. As that gets bigger, the bond strength gets weaker because the further apart ions are, the more weakly they interact. Now, there's a slight difficulty. Lattice energies are very difficult to determine experimentally directly, so they're normally determined indirectly using this thing called a Born-Haber cycle. And what happens in a Born-Haber cycle is you break the formation of the ionic compound down into several steps, and the energies for those individual steps are easier to measure than the lattice energy, and then you add them together and use Hess's law to give you the lattice energy. So typical steps that people will break this down into will be sublimation of the metal, because remember, an ionic compound is always going to involve a metal and a non-metal. And most metals are solids, so we need to get it into the gas phase. Loss of electrons by the metal, right? The ionization energy, because we need cations. Many of our non-metals are diatomic, so often we have to break them into individual atoms to get individual atoms of the non-metal. That's going to involve the bond dissociation energy. And then finally, we need to generate anions, so our non-metal is going to gain some electrons, and that's described by the electron affinity. So you do need to know, like, what do I mean by sublimation? What do I mean by ionization energy? What do I mean by bond dissociation energy? And what do I mean by electron affinity in order to solve these problems? So if you don't have a firm grip on those topics, then perhaps go back and review them. So this is a good example. It's the formation of sodium chloride from its elements. So whenever we write a formation reaction, we always generate 1 mole of the product. And so when we form sodium from its elements. Sodium is sodium chloride from its elements, and sodium is a solid at room temperature, as are all metals except for mercury. And then chlorine is a gas at room temperature, and it's also diatomic. So if we're going to form 1 mole of sodium chloride, we're going to need half a mole of chlorine. Now, typical for ionic compounds, because we're forming a very strong ionic bond, this reaction is overall exothermic. It releases a bunch of energy. So bond forming is typically exothermic. Okay, we can break the formation of this reaction down into a series of steps. So on the left, I've written all of the bond breaking processes. And they're all, as you can see, or as you will see, they all require an input of energy. And then on the right, I've written all of the bond forming processes, and they're all going to release energy. So that's why they're all described by downwards pointing arrows. So the first thing that I'm going to do is I'm going to take my sodium and I'm going to sublime it. That's step 1. And so the energy I have to put in to do that is called the enthalpy of sublimation. The next thing I'm going to do is I'm going to take my chlorine molecule, my half a mole of chlorine molecules, and I'm going to break that apart into individual chlorine atoms. And the energy required to do that is 1/2 the bond dissociation energy for chlorine. Now, it's 1/2 because bond dissociation energies are always described per mole. The next thing I'm going to do is I'm going to take my gas phase sodium atoms and I'm going to remove the first electron to create sodium cations. And the energy required to do that is the ionization energy, and in particular, ionization energy 1, because it's the first electron. Okay, so we're almost there. We almost have a gas phase cation and anion. But what we've got to do now is we've got to add some stuff to the chlorine. Now, because I'm forming a bond, I'm going to hop on over to the right-hand side and I'm going to start heading downwards. I'm going to kind of almost begin again. So I've just kind of like copied these guys over to the right-hand column here. Still got a gas phase sodium. What I'm going to do now is I'm going to add an electron, bond an electron to the chlorine atom to make the chloride anion. And the energy that's released in that step is called the electron affinity for chlorine, and we call it the electron affinity 1 because it's the energy to add the first electron. So at this point, I have a gas phase cation and a gas phase anion, and what they're going to do is they're going to snap together and they're going to form the compound sodium chloride, and the energy that's released doing that is the lattice energy, which is what we're interested in. So the energies for steps 1, 2, 3, 4, and 5, when added together, are going to be the same as the enthalpy of formation, that is, of going in one step from the elements sodium and chlorine to the compound sodium chloride. So that's what this slide summarizes, is if we add together the energies for steps 1 through 5, then we'll get the enthalpy change for the overall reaction of sodium reacting with half a mole of chlorine to generate 1 mole of sodium chloride. So let's see how we can extract the lattice energy out of this. So we know the enthalpy change for forming a mole of sodium chloride is equal to negative 411.2 kilojoules. And then we also know that is the sum of the energy changes for our 5 steps. So we can just reorganize this to get an expression for the lattice energy. So if I know this, 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 I can now get my lattice energy. So I have to look all of those values up, which I can do. And there we go. we put all of those numbers into our expression for the lattice energy, and we get a value. And lattice energies are normally big negative numbers, so I'm pretty happy with that value. Now, it's important to realize that this will not always be your formula for calculating the lattice energy. It's going to depend upon the coefficients in your equation, and it's going to depend upon the charges of your ions and how many electrons you need to add and remove. So it's not always going to be the same every time, but the principle will be the same every time. Okay, so that concludes the video for section 7.5, which is concerned with the strengths of ionic and covalent bonds.